Okay, for everyone, so we're going to be looking today at carboxylic acids and esters. So these are two more functional groups. Okay, so they're kind of put together because they're very similar in terms of structure of what the functional group looks like. They are different, of course, you're going to see that, but they're similar. So it's kind of like aldehydes and ketones, right? They kind of group functional groups together that they have similar things going on. So over here we have an example of a carboxylic acid. Okay, this is where you have a carbon double bonded to an oxygen with an OH group attached to the same carbon double bond O. In other words, it's a carbonyl or carbonyl group, the C double bond O, and there's an OH on the other side. Now on this side of the carbon you can have other carbons, so it's like an R group, or it can be a hydrogen. Really what you need to see is the C double bond O, OH. And actually sometimes you'll see for short, it will be written as COOH to represent this group. So this is called a carboxyl functional group. So when we say we have a molecule that has a carboxyl on it, this is what we're referring to. Over here are ester. An ester is where you have a C double bonded to an O, an oxygen, and there is an oxygen attached, but there is no hydrogen on the other side. So meaning there is more carbons. So it's similar to a carboxyl, except this is not an H, it is any carbon-based group. Okay, so here we go. So we'll talk about carboxylic acids first, and then we'll take a look at esters. So carboxylic acids, as I mentioned, so here's that short form for that carboxyl group. So you now have a different functional group than what we've seen so far, right? So we've seen carbonyl groups, we've seen OH groups, but we haven't seen this combination with the C double bond O and the OH. So this actually is very common in acids. So if you look at the name of the functional group, it's called, I should say this type of compound, a carboxylic acid. So just like you would assume an acid with a pH lower than 7, generally that's what you're going to find here. Now they are found naturally in a lot of different items that we actually eat. So things like citrus fruits, so oranges, lemons, limes, crab apples, rhubarb. Usually when you have fruits or vegetables that have a sour taste to them. So obviously you're probably thinking, well, oranges are sour, but they're also sweet. So obviously there's multiple compounds that are found in these living things, right? It's very complex. It's not like it's a pure substance. But that sour taste is attributed mostly to carboxyl-based groupings. Okay, so looking at carboxyl groups, so they're always at the end of a chain, or I guess you can think of it as the beginning of a chain. Just like how aldehydes were, the carboxyl carbon is assumed to be carbon number 1. So let me show you an example before we start talking about intermolecular forces. So regardless if I have my carboxyl group on the right or the left, this carbon is carbon number 1. So if I had it the opposite way, it would not matter. Carbon number 1 is always your carboxyl group carbon. Now, when you're looking at the properties of these structures, we have to now consider the polarity, of course. So when we add in our carbonyl group, we know that that C double bond O is a polar bond. Also, we have the CO of the OH that is a polar bond. And most importantly, and it's not really drawn great here, but the OH, right, if we were to draw this out in a little bit more detail, just so you can kind of see it, the OH is a hydrogen bond. So actually, we have now our first structure that actually will be more polar than a regular alcohol. So if I have a carboxyl group compared to a molecule with an OH on it, right? So let's assume we're comparing one molecule with the OH versus the carboxyl group. The carboxyl is much more polar because not only does it have the OH, it also has an additional C double bond O dipole. So yes, of course, dipole and LDF is still there, and we both have hydrogen bonds, but then you're comparing the number of dipoles that are existing. Okay, obviously it also depends on what else is on this molecule. So in this case, we're just simply comparing like straight up OH compared to COOH. The COOH group is more polar, which will make sense now that we're talking about this. So we know that the carboxyl group is polar and has hydrogen bonding. So molecules that have these carboxyl groups are going to have higher melting and boiling points. They're going to be more soluble in polar solvents. They'll have a higher viscosity, right? All those things, those properties that go hand in hand with intermolecular forces, you're going to see that here as well. So let's talk about naming. So naming carboxylic acids, as we mentioned, the C on the COOH group is always carbon 1. So actually you never need to number it. Similar to aldehyde, it's kind of the nature of the functional group. So aldehydes, the C double bond O is at the very beginning of your chain. The same thing is happening here. So you are basically finding the longest continuous chain of carbons, but being mindful that that has to be your carbon 1. So the suffix change is actually oic acid. So instead of butane, so here we have 1, 2, 3, 4. So this is butane, raised 4. But this is now butanoic acid. So your ending is now oic acid. We do not need a number. Okay, so what happens if there are branches coming off of that carboxyl chain? You don't need to put the number 1 for the carboxyl, but of course you'd still have to number everything else. Let's do an example. I'm even combining different functional groups. Look at this. We've got 1, 2, 3 different functional groups. I know we have a benzene branch here, but that's technically just a regular hydrocarbon. Okay, so let's start taking a look. We have to start numbering. So carbon number 1, 2, 3, 4, 5. So we now have our parent name is pentane, but now this is going to be pentanoic acid. Okay, so there's our parent group. We don't have to indicate the number 1. If you ever forget and you do put the number 1 in, that's fine. It's still correct. I'm just saying that when you're reading a name of a carboxylic acid, you're going to notice they never put the number 1. Okay, so then we have some branches. So we're going to have to name these in alpha order. So we have a bromo. We have a phenol. Remember that phenol is benzene as a branch. And we have here a methoxy. So remember when we learned about ethers, they're named as branches. So we have a methyl branch, but there's an oxygen in between. Okay, so we're alpha order, so we're going to have bromo first. Okay, LMNOP, so my methoxy is coming next. So we have 4 methoxy. And then we're going to have a 3 phenol. Okay, so that's kind of squished in there. But the 3 phenol would be written before the, actually we don't even need this dash, pardon me. because there is no number. So it's just 3-phenyl pentanoic acid. Okay, so what about if I have an OH group on it though? Let's talk about that. Let's do an example. Okay, so now when you are doing numbering, normally your OH group takes priority for numbering purposes. Actually, let me move it over just to make this point, drive this point home. Okay, so the OH, so normally if this was anything else, like let's say, I don't know, this is just a carbon with hydrogens, normally you would start counting closest to the OH group. But we have a carboxyl. Carboxyls are now our new kind of functional group royalty. Okay, so the carboxyl has overcome the OH's priority. Okay, so first time seeing that. So that means this is my carbon 1, 2, 3. So here we have propanoic acid. Because there are 3 carbons in this longest chain. And on carbon number 3, we have an OH group. So if you remember when we learned about alcohols, we can actually use OH, or actually we can write OH as being a branch. Okay, so personally, I find this is the easiest method. I'll show you another way of naming this. But remember that the OH group is really a hydroxyl or a hydroxy, both are acceptable, branch. So we would just simply say 3-hydroxyl. Okay, the other way of doing this is if you separate the different suffixes, pluralize, if you separate the different ones and including the OH. However, the parent functional group, the most priority, has to be the one written last. So it would look like this. So pentan 3-oic acid. Okay, technically, that doesn't look very good. I would say if you're going to separate these, if you're going to write it with a different suffix ending, perhaps include the one, just because it looks, I don't know, it looks improper to me. On a personal note, but because it's always number suffix, number suffix, number suffix if you're using this method. However, this is always the easiest way I recommend. But they're both correct. They would both be considered to be correct. Okay, so let's go back to this. So, as I mentioned, we don't need a number for the first carbon in our carboxyl. Now, you're going to start seeing more and more organic compounds being called by their common names. Okay, so we saw that already with cholesterol. A lot of carboxylic acids are also known with their common name. So, for example, ethanoic acid is really also known as acetic acid. So you're going to see this again come up time and time again, this prefix of acete. Acetyl or acete is sometimes used in place of eth. So acetic acid is like a common name for ethanoic acid. So the proper IUPAC name would be ethanoic because it would be 2 carbons with the carboxyl group. However, acetic acid is very commonly used. Of course, we can have more and more complexity here. So aspirin, which is commonly used, let's say, for if you have a headache, pain relief. Aspirin is also a carboxylic acid. And of course, we don't name this. When you go to the pharmacy, you don't ask for 2-acetyl-oxybenzoic acid. Typically, you just say, where's the aspirin? Okay, but it does have a proper IUPAC name.